having those as digital workflows is hugely beneficial for geospatial people, and all of the normal customization requests that can drive you batty, like, change this font, make this a little bigger, change this color, all of that. You're delivering base cartography, but people, as we said, can manipulate that cartography, can make the map part bigger and the table part smaller, or vice versa, right?
Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Mike Flaxman from a company called OmniSci. So OmniSci make this pretty amazing GPU-based database. We're going to be talking about GPU processing, what that has to do with geospatial. Mike is an absolutely incredible guest. He takes a very complex topic and breaks it down, makes it understandable, and towards the end of the conversation, he offers some really interesting insights into the geospatial industry. So stick around for that. Back in episode 67, I was talking to Alistair Dickinson from a company called Mapsimize, and they have generously offered to sponsor the next few episodes of the Mapscaping podcast. So I am incredibly grateful to Alistair and Mapsimize. Not only did I enjoy the conversation, but I think what they're doing with and their work around spatially enabling customer relationship systems, I think this is going to be a growth side of the geospatial industry. So if you haven't already listened to it, go back and listen to episode 67 with Mapsimize and Alistair. I think you'll really enjoy the conversation. Okay, that's the end of the introduction. Let's dive into the interview. Welcome to the podcast, Mike. Thanks for coming along and taking the time to do this interview with me. Much appreciated. You are the Chief Spatial Data Scientist at a company called OmniSci, and you guys are doing something really interesting around GPU processing. So before we dive into all of that, perhaps you could just give me a little bit of information about your background. How did you become a Chief Spatial Data Scientist?
Thanks, Daniel. It's a pleasure to be here. So I had a really long route towards this destination, but I started out in biology and got interested in land use planning and planning of cities. And so GIS and spatial systems were the best tool for doing that. So I spent quite a few years, decades actually, in teaching and working with GIS systems. And then I went into consulting, and as a consultant found that the volumes of data that I was being asked to deal with were increasing considerably, and they were getting a temporal element, which was exciting and challenging, but was blowing up my tools. And so I discovered OmniSci as a customer for my consulting business. That's what led me to join initially as a consultant and then ultimately full-time to help improve the product and its GIS capabilities, as well as its data science capabilities. So it is an exciting time because these things are all merging and changing.
So you had this problem. You were living in an exciting world, lots of data coming at you, time series data as well. I mean, this couldn't be better for a data scientist, for a spatial data scientist. This is a great time, but you're running into a wall, and that wall sounded like it was the processing power of the tools that you were using. So perhaps we should start there. How is OmniSci solving this problem? What is it about their technology that's helping you out, or helping people like you out with large amounts of data?
Sure. So if you think about kind of basic computer architecture, if you're lucky, you might have 20 CPUs. If you have your average gamer's graphics card, you might have 20,000 GPU elements. And so GPUs just have orders of magnitude more processors. However, they're not as general purpose as a CPU. They like to do little discrete bits of work that are more or less the same weight. And so if you can figure out how to subdivide a problem into 20,000 pieces of equal weight, they will do it in less than a snap of a finger. And so GIS data often has that characteristic, but not always. So in GIS, often we're dealing with raster pixels, for instance, and we want to do some bit of logic across layers that's equivalent for each pixel. Or similarly, in the vector side, we've got geospatial features, and let's say we want to buffer them. Well, the first step in buffering is independent of other features. So we can do a lot of that work in parallel. So essentially, the idea is to use GPU to accelerate database operations and then geospatial database operations. And since you've got a lot more processing units, you divide the work into much finer grained pieces. And I guess I would add that I'm not a GPU programmer, never had that background. Those are brilliant folks. What I liked about OmniSci is that it makes that power accessible to you with regular old SQL. And for those that know PostGIS, it basically uses equivalent syntax to PostGIS. So if you want to buffer something, it's stbuffer. You don't need to know all of the secret sauce that goes into running that on GPU. You can ask a query and get just a snappier response, 10 to 100 times faster than conventional GIS. So those are, I think, the two elements are kind of ease of use, but on the back end, leveraging the power of these graphics processors that we all have increasingly on our personal machines and certainly in data centers in huge numbers.
So you mentioned the back end there. So this sort of tells me that there's some kind of stack involved here. Could you maybe briefly describe what this stack looks like? Break it down into its pieces for us?
So OmniSci is basically a 3-layer product. The core of it is an open source database that can do geospatial operations and, as I just mentioned, speaks SQL. There is a rendering layer above that, and the rendering layer is a special purpose renderer on GPU. So it can take the results of a query and render it in situ, and it can handle billions of polygons or billions of points rather gracefully, millisecond rendering times. And then there is a dedicated front-end tool that's called Immerse, and that is a React dashboard app. And so from an end user perspective, most of your experience can be in the Immerse environment, and it's very much a dashboarding environment. So you add maps and data and various chart types. And what's nice about it is there's no programming required, but everything is wired together. So if you put a histogram and a map on the same dashboard and you select something on the histogram, just like you might expect in GIS, that selection propagates. And that works for large numbers of chart types. So it allows people with very little geospatial background to create dashboards that are useful for their particular workflow. It does require, of course, on the back end that some people with geospatial talent have put together the right data in the right coordinate systems to feed that front end. But that's essentially the stack. So there's a front end dashboard environment. It speaks to the back end essentially in SQL. There's an additional SQL call that's kind of a render map call. And so you can either get back from the backend database query results in the form of tables or rendered results in the form of maps and charts.
So I'd like to focus on that backend database for a little bit, because I think a GPU-based database is interesting in itself. And you also said that this was an open source product. So that's really interesting too. So everyone has access to this if they want. Can you talk a little bit about what it's like to use this database? What is it like to push data into it? You said that it speaks SQL. As a user using this, will we just experience the same sort of level of interactivity as what we would with a normal spatial SQL database? Does it look different? Does it feel different? Is it hard to push data into it?
So on the data import side, the news is good for geospatial folks in that all of the major geospatial types are direct imports. And so you can bring in shape files and Esri file geodatabases, for instance. You can also bring in GeoJSON or CSVs that are quasi-spatial or text-based spatial formats. And so those just directly import and show up on your map just as they might in GIS. The additional part that I think is quite useful for large data is that you can not only point to data on disk, but you can point to data on remote cloud services such as S3. So for instance, if you have a huge bucket of shape files sitting on S3, you can directly import those, and you can do that from your iPad or on a low bandwidth network. Doesn't matter, because that's being done directly from Amazon to OmniSci. And so on data import, it works quite a bit like a conventional GIS. And then in processing terms, I guess there are two levels. So if you're just stacking map layers, that again works like conventional GIS. You can add in any number of map layers from any number of sources. There are additional data types, however, and so the most common ones are various tabular databases. So there are ODBC connections and JDBC connections to various backends, and there are streaming connections. And so you can, for instance, attach to a Kafka streaming server. So imagine you've got event data from, let's say, GPS feeds coming in. So you might put those through Kafka, and those things then get updated on your map on a streaming basis. So in any case, like GIS in that first experience, but with a broader diversity of data types. And then I guess, as I probably should have mentioned, it's temporal, not just geo. And so for everything that has a geo timestamp on it, there's special magic that happens on the front end, essentially, that can integrate things on time without any programming. So as long as the timestamps in the data are ISO or can be made into ISO timestamps, then you can integrate things on time and put in a timeline and animate things over time.
So we've got this incredibly powerful, incredibly flexible GPU-based backend that speaks SQL. And you talked a little bit about the start about the stack, and you said that there's a dashboard. Are there any other user interfaces I can use to query this data to get it out? Can I plug it into, or can I point ArcGIS at it, for example, and use it in that way? Can I, other sort of standard GIS tools, do they have an interface to the database?
I guess the main interface I would highlight that's a bit of magic glue as well is that there is built-in Jupyter Notebook integration. And so for everything that you create in OmniSci, you can literally hit a Jupyter Notebook button and flip over and look at it from the data science point of view. And so there you're in a scripting environment, but you're already authenticated and you already have kind of access to the tables that you've just seen on your dashboard. And so then you can get to those tables with a whole variety of Python-based tools. And those can include, for instance, Esri libraries to push and pull things into the Esri universe, or OpenGIS tools for pushing and pulling from things like web feature services. The tool is able to speak to this Python notebook environment, and through that to a very large diversity of additional data science and GIS tools. But that's the normal generic way of connecting things, I guess, if just importing and exporting files is not sufficient. You can, of course, import and export files. The other thing I probably should have mentioned is that, as you would expect with any web mapping tool, you can add OGC web map services as base layers and have any number of those available. It can consume OGC data in that format as well. I've done a number of projects in which I either export data or create essentially a web feature service to stream data out. A lot of things there depend on the data volume and the specific problem. But you can think about this as a kind of GIS temporal accelerator layer. And if there is utility in getting the data back out as raw data, you can do that. Most of the time, however, because the data volumes are huge, it makes more sense to render things on the back end and, for instance, render map tiles and consume those on the front end side in your GIS, for instance.
This is not a criticism in any way, shape or form, but it sounds like a pretty standard database so far. But like we keep talking about, this is a GPU-based one. So can you talk a little bit about that? Right at the start of the conversation, we talked about if we want to render features or process features in parallel, that this was a huge advantage doing it on the GPU. I'm really interested to hear a little bit more about that. Maybe we could start off by talking about the differences between CPU processing and GPU processing, just so everyone has a good understanding of what we're actually talking about here.
In traditional CPU processing, your software, often written for a single CPU, goes through your file essentially top left to bottom right, if it's raster, and it performs a sequence of operations on every pixel, let's say. In a GPU database, there is a direct access path from the file to GPU, so that's something handled by the graphics card, and you're then issuing commands to the GPU to do something, for instance, with every pixel in its buffer. And so the difference from a GIS processing point of view is in that parallelization. And then to help that along, I should say there's another style difference that I've found in working with these systems. The most expensive thing in both CPU and GPU is usually these days not necessarily processing, it's data transfer. It can take a fair bit of time to stream your huge file onto your CPU, and that time is significant, and you want to kind of avoid going back and forth. And so my workflow used to be in GIS a lot of cases where I would save intermediate file results and then have to manage all of those intermediate file results. What I find myself doing on a GPU database is to create a series of views, and then those views are evaluated on demand. So it's a kind of lazy evaluation. And you can very quickly create a whole stack of views. You can preview any of them to make sure you're not going off the rails, you're getting the expected results. But then you can essentially do set up a workflow with a very large process And you can be doing that either by looking at a piece of it or looking at the whole. When you zoom out in OmniSci, you're actually computing a subset of the visible pixels first, and then you're computing the rest of them. It's a workflow that kind of keeps things interactive. You can make sure that you're getting everything right visually, but what you tend to want to avoid doing is writing everything to disk or writing all those intermediate files to disk, because you can just let the GPU database manage the set of views. And when you've got something that's good, you then persist that to disk, obviously. And that command history is all aggregated on the object, so you don't lose the ability to go back and edit. But essentially, I find myself doing a lot more exploratory data analysis interactively, making sure I've kind of looked at every corner of my data and I'm certain that the analysis is working correctly. And then persisting to disk is less common than in traditional GIS. So traditional GIS, you're doing kind of one operation at a time, or you use something like a model builder in Esri software to build a workflow. In GPU database, you're doing a lot more stuff visually. And the persistence, of course, is a database, so you persist things ultimately. But it makes good sense to avoid doing so until you need to, because the database write is the slowest part. Everything else is pretty much interactive.
So it sounds like we have a lot of power here, and we can process things in parallel. And right at the start of the interview, we talked about an example there. And I think the example was something like if you had 20,000 polygons and you needed to do a buffer on all of them, well, that could be done, without connecting them. That could be done individually on each polygon. And if you have a GPU with 20,000 cores, well, there you go. And I think people would refer to this problem as being embarrassingly parallel. So this is a really easy to understand workflow, straightforward. What about in situations where it's not embarrassingly parallel, where it's difficult? Is that complexity, is that handled by the database itself? Is that something that the user needs to think about, or do they just write their command in SQL like they always would, and the database looks after the rest?
I guess there it depends a little on the complexity of the geospatial problem. So an example is I just did a project with a major telco, and it was line of sight analysis and radio frequency mapping. And so in that case, we are casting tens of millions of rays from cell phone towers out into the landscape. Each ray operation, the initial steps are embarrassingly parallel. So for each ray, you look at what it intersects. Is it going through vegetation? Is it going through building? Is it going through free air? But the next step is order dependent. So if you want to look at the fall off of frequency, you essentially need to do that in the order that the signal would follow from the antenna to the destination. And so that's in GIS would be something like a cost distance function. In OmniSci, that's a window function in the database, and window functions, the name comes from database history, and so is very different than GIS. But essentially, windows there being windows on a 1D line, and so you can do something like a cumulative sum. Those things are built into the database, and it is a little different than the traditional GIS operation. But if you learn and use that function or that set of functions, essentially, you can operate in parallel on many thousands of features, but with a sequence of operations on each feature. And so that's slightly different setup than in traditional GIS, but if you do it that way, you get the full benefits of parallelism. So in that case, you do think a little bit about the staging. And then there are other operations that are just hard, right? So an arbitrary viewshed analysis or any other global operation in GIS ultimately needs to look at all the data. And so those things essentially work the same in OmniSci as they would in a conventional GIS. They do benefit from the underlying platform speed. It is just a modern platform that's faster. For instance, parallel reads and writes from disk. So you get some benefits under the hood that you don't need to worry about. But ultimately, if you're doing a global operation, that is on the lower end of performance of OmniSci. But it's usually, my rule of thumb is 10x faster than conventional GIS. So it's considerably faster just because it's running on this super modern platform, even though the speed ups you get for the embarrassingly parallel stuff are 100x or more. So it's relatively slow because it's got to look at all the data, or it's got to get all the data onto GPU. But it's then in that case just the same operation as you might do in GIS. So you set it up the same and you get a little bit better performance, substantially better depending on the size of your data, but not crazy better the way you do with some of the embarrassingly parallel operations as you describe them.
Yeah, but I mean, those are also operations that are just so obvious that, hence the name embarrassingly parallel. You don't need to do anything. They're parallel by nature already. And I think even if you're getting a performance increase of 10x, that is still pretty incredible.
It's quite good, and it does change the way you think about doing a lot of things, because things that used to be too heavy to do accurately, for instance, you can crank up the accuracy threshold, right? So things you might have generalized or smoothed before, you can take on.
So in a previous conversation, you gave some really good use cases for this, and it was a lot of it was focused around LiDAR data. I wonder if you could just take the time to walk us through that, what OmniSci can do for folks that are dealing with large amounts of LiDAR data.
One of the most fun projects I've had a chance to work on for OmniSci is for a major California utility that has hundreds of thousands of miles of power line. And as would not be surprising to anybody, they've had issues with fire, and specifically fires caused by the contact between vegetation and power lines in high wind events. And so we built a power line fire risk model for them. And it was an interesting project because it took in LiDAR data to describe the physical structure of the trees, also remote sensing data to get at the vegetation health, and wind data, both historical forecast and current, being a kind of major contributing factor. So essentially the risk of a tree falling over goes up with the square of the wind speed. So you definitely need to understand the variation in wind speed, but that's being applied then to data that you extract from LiDAR. And so let me describe a little bit of the LiDAR use case there. So that utility had contracted with a third party to develop their LiDAR data, came in the form of 5 million individual LiDAR files sitting on an Azure blob store. And so immediately you have a kind of difficult to manage data set. We were able to import that data and do analysis on it, for instance, to extract out vegetation from power lines, and then look at the spatial relationship between the vegetation and the power lines at scale. And that process was done analytically very similar to the way you might do it in conventional GIS. It's just that having that scaling ability meant we could deal with a data source that was tens of billions of LiDAR data points. And so we ended up, for analysis purposes, binning them into 1 meter slices. And so a tree became a set of 1 meter slices, because the main physics model for describing how trees interact with the wind is a kind of pendulum model that wanted to know the weights of things vertically. So we sliced the world into 1 meter by 1 meter. I'd call them voxels, but they were hexagons, so I'm not sure what to call them, hex voxels. And then we're able to apply something like a wind attenuation function to all of those voxels in parallel. And so you can take the direction of the wind and say, what if the wind moved from the south to the northeast? And what if it increased by 20%? And you can look at the output risk model in real time, calculated against those billions of features. From a GIS perspective, underneath the hood, it's a risk suitability analysis model that anyone would be familiar with. Basically a regression run against historical data of how these different factors contribute to risk. But from the user experience point of view, it lets you get ahead of the fire, right? So you've got a risk model that can not only show you current conditions and update as frequently as your data comes in, but you can also use it in a scenario forecast sense and say, what if the wind shifts? What if we deploy resources over here and not over there? So we talked a little earlier about use cases. I think one of the major contributions to having this kind of super speed and scale is that you can take forms of analysis that were traditionally done as a kind of project that you would deliver on, often in paper reports, and you can make it into a real-time dashboard that's showing current conditions, or into a scenario tool that lets people change what they can manage and confront, what's going on in the live environment. So I just gave you an environmental example, but you can find similar examples on the factory floor, right? So in cases where traditionally you might have built a static model and delivered that one off, you can now deliver a data science workflow or spatial data science workflow that can respond to changes in events. So I think that's a really exciting, new area for GIS people to get into. because those use cases are really high value. They're very socially and business useful, but they rely on the spatial analysis skills that a lot of folks already have. It's just cranking it up by bringing in this real-time component and the ability to then deliver that out to enterprise quickly.
So I want to highlight a couple of things. First of all, it sounds like an incredibly complex model. I mean, if you're slicing the world into those sort of flat voxels, I guess we could call them, and then calculating the movement of every tree along those length of power lines, I mean, that's pretty complex in itself. And then doing that in real time, I mean, this is a huge undertaking, I'm assuming anyway, and it sounds like you could achieve it relatively quickly. I just want to clarify, how were people getting access to this data? Was it through a dashboard, or was it through some other kind of interface? Was it an interactive kind of thing?
That particular case, there were actually different subgroups within the utility that wanted access in different ways. So first off, they have a very good data science group internally. And so they wanted analytic access, and they got it through dashboards, so Jupyter Notebooks running Python in their case. But there was a whole vegetation management section of the enterprise, and they wanted the ability to zoom into the high quality visualizations, actually in their case looking at the full detail raster data, because they could see things in that data that you and I couldn't see. They've spent decades dealing with tree Powerline interactions, so they want to look at the model in considerably more detail, but they're usually looking at it visually and prioritizing or designing a work program, looking at the data and bringing in obviously some of their internal knowledge of locations and areas, so stuff we don't have in the data, they have in their head. So they're combining those two things and setting out a work program, for example. So the delivery for them was through dashboards that could render all this LiDAR stuff on the back end, but be accessed through a normal web browser. And that was a interactively intense engagement, but it was serving a built model. And then the back-end groups tasked the data scientists. They're responsible for building and updating these models. And so their interaction, they use the front end also, but for kind of feature engineering and feature discovery, right? And to make sure their model is still on track and still performing. But they're typically going with a Jupyter-based workflow and then flipping over to the interactive graphics to check that the model is performing correctly or the data is good, and then flipping back and doing stats or data science on it. So I guess I would point out those two groups, because I think that's fairly common in enterprise these days. I mean, you have a technical group that's building and maintaining models, but you have business work groups that are applying and deploying those models.
Yeah, and I think it's incredible that each group of users had their own way of interacting, right? So there was people that needed certain messages, certain kinds of access, and they got it, but it's all based on the same data, the same model, essentially. So I think that's absolutely brilliant. And I think that's probably going to be the future, right? Like where GIS isn't happening in a silo, geospatial stuff, analysis isn't happening in a silo. Other people are going to want access to it, and they're going to have different use cases or different ways of using and consuming this data.
Yeah, no, I think that's true. And it's both empowering and maybe a little unfamiliar to GIS folks that are used to fully delivering the product in cartographic format. Because in a way, you're designing a user experience, right? So you're giving somebody access to the geospatial data and your preliminary cartography, but you're giving them the access to a dashboard. And so they take it from there. And if their job is, workflow order management for vegetation contractors, they're going to use what you built, rejigger it to make their workflow optimal for what they do day to day. So you're essentially building a kind of template or base geospatial dashboard, but in a context where a lot of people are going to customize it for a lot of different purposes. So I've seen a little bit of this in local government. When I worked for Esri, we had a lot of people that would take a template in JavaScript and customize it. The difference here is those tools are getting much more mature and much quicker to deliver. And so you don't need to fiddle with JavaScript. You can basically use a mature GUI to generate those dashboards. And not only can you do that, but the end users can do that. So they're often reconfiguring, for instance, the size of charts. As one thing I've noticed is nobody can agree on what the relative size and position of the elements should be in one of these dashboards. And that's a good thing, right? Because it just means that people are optimizing it for what they want to look at and what they need to look at. And it also means from the GIS professional's point of view that you can concentrate on making sure that the data and models delivered are the correct ones and the initial cartography is good, but you don't need to manage the app development process. So I found a lot of folks in local government in particular were getting dragged into app development, and it wasn't entirely comfortable to them, right? So they're having to do a lot of work on JavaScript and user interaction, callbacks, all that kind of stuff. I think it's a better use of GIS people's skill to be focused on getting the next best model out there and the next generation of better geospatial data and analysis. So I think it's a more comfortable division of labor if the end users have more power to reorganize their dashboards as needed. And the delivery mechanism is essentially, you saving your dashboard and setting the permissions to share. So it's quite easy from the producer's point of view. And of course, underneath is a database. So if you want to version things and deploy things carefully, you have that capability. So you can actually run, multiple versions of dashboards that are driven from multiple generations of data if you need to be cautious about that. That's also a use case for government where they need a record of decision. And so they need to be able to archive and show, we made this decision on this date, given this information in front of us. So, in any use case where you need that record of decision, I think that's important to have the data management capabilities underneath to do that. So you're versioning not only data, but versioning interfaces or dashboards on that data, and increasingly data science models as well.
Yeah, but I think this is also really important, right? If we are giving people the power to change the dashboards and manipulate the data itself, then I guess having that record, that documentation of, well, what did the dashboard look like at that time? Because if people are going out and basing decisions based on the data and a dashboard that they've manipulated in some way, shape or form themselves, I think having that record to go back to and say, oh, well, that's why. Maybe that decision didn't look like what we expected, but perhaps it was a result of the dashboard itself at the time, not just the underlying model. So I completely understand that. I just want to highlight something that you said that I found really interesting, was that you mentioned that we were no longer just providing this deliverable, this result, but we were actually designing user experiences. And I'm sure a lot of geospatial people breathed a sigh of relief when you said that the users were empowered themselves to design their own dashboards, because designing an experience, a lot of us out there would have heard, oh no, now we also need to be app builders as well. We need to be developers, and dealing with that education around, okay, I've created a model and this is what the user interface looks like. This makes sense to me. But then going out into the world and delivering it to the end user and saying, there you go, use this thing here. And then that iteration around collecting feedback and designing that experience. I mean, it sounds like an art form unto itself.
Yeah, no, it's a great point. And, anyone who's been in geospatial as long as I remember versioning, doing public meetings with maps, and we'd get out into 17, 18, 20 versions of something before it would be approved, right? And it was all done on paper and plot with a really long round trip. So it would take us, often a week to get back in front of the stakeholders and present the next version of something and get it batted back and forth. So I think having those as digital workflows is hugely beneficial for geospatial people, and all of the normal customization requests that can drive you batty, like, change this font, make this a little bigger, change this color, all of that. You're delivering base cartography, but people, as we said, can manipulate that cartography, can make the map part bigger and the table part smaller, or vice versa, right? And so by just giving them control over those end use format issues, still need to give them a decent cartography to start with, but you're able to accommodate a lot of downstream customization. Essentially, you don't need to worry about that part. You just need to worry about the initial experience being good so that people see all the data. Often, when I'm delivering such a thing, you have to be careful about map scale. That's, I guess, general with delivering anything on a dashboard these days, right? So you need to make sure when people zoom all the way in or all the way out that the cartography still works, right? But once you get beyond that, I'm pretty comfortable these days in passing along those dashboards. And the other piece to it is that it alleviates a lot of the demand for custom apps, because if people have that ability to customize themselves, they will not be coming back to you immediately for a custom app. The custom app becomes, there's still needs and use cases for custom apps, but they become less frequent if the user can can do a reasonable customization. So I think about it as, the non-spatial equivalent might be delivering something as a well-formatted Excel document, right? And so, yeah, people can customize that. In the case of Excel, it's a little scarier because they can break the formulas. But in the case of a dashboard, you still maintain control of the business logic part. They're mostly just controlling the cartography and layout. So I think that's a reasonable division of labor. So you make sure that, the geospatial analyst has done the stats right. You don't want the users trying to redo the stats most of the time, unless they are data scientists, but you're able to deliver something that can go out to enterprise. And so I think that's a key benefit of delivering in dashboards. And it's a new experience to me. I'd spent my life delivering paper map plots for the early part of my career. But I do think it's a key business benefit for GIS folks because it gets more people more engaged with your work.
Absolutely. And I think, too, it really speaks to that idea that not everyone is going to need the same message, that we need specific messages depending on who we're dealing with, and people need to see specific things and will have specific needs. And, this idea of customization, as well as like keeping it within a box, right? So, yeah, you can customize it, but we've designed the environment you can customize within. So we've tried as professionals to make sure that you can't make too many mistakes. At least that's what I hear you say. I'd kind of like to move off now and talk a little bit about the future, because this GPU processing, it sounds really, really exciting in terms of dealing with massive amounts of data. And I'm just wondering, is this the mic drop now? Like, I have to use a podcasting analogy here instead of a sports analogy. Is this the mic drop? Is that it? GPU processing, this is the last word in terms of spatial processing. Do we need to use CPUs again?
I think there are still use cases for CPUs, but they are where the data scale horizontally is so enormous that it doesn't fit modern GPUs. I think of OmniSci as being kind of accelerated data analytics, but you can indeed sit it on top of a data lake. One thing we hadn't talked about before is some new work. So this is future, but OmniSci is actually working on a foreign storage interface. And so the idea there is to be able to point to data at rest inside a data lake, for instance, and just extract out the bits you need to generate a particular analysis or dashboard. Typically with GPUs today on a large GPU server or cluster, we're handling 10 to 100 billion rows of data. Once you get beyond 100 billion rows of data, then you're currently in a territory where you do need Spark or you do need some scale out horizontally to synthesize data. And so I don't work on many use cases that are above 100 billion records, but I'm sure there are people out there that are doing that. So there's still that universe, and that borderline will continue to shift over time, I guess, as the different technologies shift. But I'll emphasize once again the open source benefit on the OmniSci database core is since it's open source, you can move and install it wherever the heck you like. And if you're smart, you'll move it to where the data is, if the data is big, right? Because you can then get the analytics done close to the data. And maybe a good example of that is I work a lot with Sentinel-2 data, which is from the European Space Agency. That happens to be hosted by AWS in Frankfurt. So where do I do my data processing? Well, AWS Frankfurt, of course. So, I move the software to where the data is so that I have that capability then to do the analysis close to the data. And I think as the data volume get huge, we have to think differently about the relationship between data and software, right? It's changing. But I do think the future is that you move your tools to where your data is more frequently than not the inverse. You don't start a project by moving all the data to you local because it's too crazy big. You didn't want it anyway on your desktop. It's a complex universe out there. All these tools are changing all the time, but we are getting to the point where moving data to your software is definitely a bad strategy, increasingly bad strategy. So whether it's with GPU accelerated technology or CPU scale out, you're probably going to be doing that close to where the data lives. And then for your interactivity, everybody, I think, following this conversation already kind of realizes that having the power of GPU to render the stuff makes a lot of sense. The observation from OmniSci in that architecture is it often makes sense to render the data also where you've done the analysis and just send the interactive visualization to the client. I think that's one future direction. Obviously, machine learning, we're doing a lot of work on better ways to bring in messy geospatial data. And so I'll talk about one other project here in that regard. So we had a client who's a nonprofit that does open source intelligence, and they were looking for nuclear missile sites in North Korea. Well, you don't get a map with those, so you got to do the analysis work. Their analyst had discovered by looking at the data that dead-end roads that end in mountains that appear to go nowhere are a pretty good intelligence tell for where a nuclear missile site might be. So they wanted to do an analysis of where all the dead-end roads in North Korea were. We partnered with Planet that has a new product that's applying machine learning to their daily planetary imagery, extracting out roads, and in their case, both roads and buildings, but we use the roads here. So we took raw remote sensing data, extracted out roads. In our case, we had them changing monthly, and then we did a suitability analysis based on which roads were changing over time. But the part that's new there, I think, is fronting GIS with machine learning, right? So you've got this raw data out there. You're using machine learning to do the interpretation to extract features out, and then you're building an analysis on top of that that's iterating. So I see the immediate future a lot more of that, and we're building tools to better integrate those front end uses of machine learning in our process. So right now, a lot of people are using us on the back end to do the machine learning once you have the features built, but we're also looking at machine learning to help build the pipeline of current geospatial data.
Thank you very much for taking the time to clarify some of those things there. You said a lot there, and what I guess really stuck out for me was that there's no real one answer. There's no silver bullet here. It really depends on the situation. I really like that insight around moving software to the data. I'm with you on that one. I think that's the future. I'm curious though. So we've said that GPU is going to be one of the toolboxes, or one of the tools in our geospatial toolbox going forward. What does this mean for practitioners in the industry? Does this mean we have to go out and learn a whole bunch of new skills? Or do you think that as these tools develop, that complexity will just be hidden away from us as users?
So I guess there's probably a meeting in the middle. I would say that the biggest change, at least that I personally experienced in this new world, is the temporal side. And so, I was trained in traditional geospatial stuff. I didn't have a lot of courses or background in time series analysis, but a lot of the, let's say, the Sentinel imagery we just talked about, that's every 5 days roughly. So you end up with a 4-year time series of imagery. And so the thing that's new there educationally, it's not that there aren't people in the world that can teach you how to do time series analysis. It's just that geospatial traditionally hasn't had to deal with temporal. So I think analytically, that's the new part, is dealing analytically with both space and time. But the tooling for that already exists in those two domains. And of course, the messy part is whether you can get it to interoperate, right? So OmniSci has got some of that, and certainly on the interface side has that. But analytically, it's a really deep area. So there are deep learning models that only work on time series, for instance. There are others that only work on snapshots, but work spatially. So I think that as we move forward, in terms of skill set, the most important thing probably is to add temporal to your toolkit if you're not already familiar with it. The access to the underlying tooling, that stuff is kind of moving to you, so you don't need to move so much to it. But then the other piece that everybody is probably already aware of is kind of the change in data science is that you're using machine learning to extract value from information. Often when you don't get the expected result, the answer isn't to change the model, it's to change the data. And so that's something I think GIS people are very good at and very aware of. But it's interesting, right? So you're not spending your time necessarily building a better technical model or changing the model architecture. At a certain point, once you've got the right model architecture, you're changing the data. So, a number of cases have come up famously in data science where the models are giving inaccurate results. And it's almost always the case that the training data was biased in some way that people hadn't spotted initially, right? So I think that that's going to be as true in geo as anywhere else. And we need geo people that are able to pay attention to that stuff and use the whole set of tools already in their tool belt to make sure that the data that's provided to these models is correct so that we're not training them on nonsense. So I think that It's not entirely new, but that's going to be an aspect of the relationship between geo and data science for the coming few years. So we've got a bunch of people being trained in data science, but not having a background in geo or all the analytic tools that we've got in our field. And so as we engage with them more, the common ground is high quality data, right? And training data especially. But training data, those models are really hungry for data, right? It's not like a regression that you can train on 12 samples. They are models that want 1 million samples. And so geospatial folks, I think, have a good idea of how to provide those 1 million samples, but also some sophistication about making sure that there's quality control on that process, that the stuff we're training machine learning models on is valid data. And so I think we've got a lot to contribute in that field, but it's going to be a long-term interaction, right? This stuff is going to be going on for the next 20 years plus, right?
Mike, I really want to thank you for taking the time to talk to me today, for taking the time to teach us all a little bit more about GPU processing and the advantages of it. And I really want to thank you for your insights into the industry as a whole. I really enjoyed the conversation. Just before I let you go, where can the listeners go to reach out to you or learn more about your work, or perhaps download this database and try it out for themselves?
In terms of the database itself, omnisci.com is the main site, and I would recommend /demos if you want to take a look and kick the tires, because there are about a dozen interactive demos, so you can get a good sense of the immerse side immediately without installing anything. And then the open source side of the software is on GitHub, so github.com/omnisci. And then if people want to reach out to me, I'd be very happy to talk to them. I'm on LinkedIn, probably the easiest way to find me. So ping me on LinkedIn.
Thanks again. I'll be sure to include all of these links in the show notes so people can catch up with you in that way. Thanks again. I really appreciate it.
Thank you, Daniel.
Once again, I just really want to thank Alistair and the team behind Mapsimize for their support. I really appreciate it. If you haven't listened to the episode yet, go back and listen to episode 67. It's all about adding spatial functionality to a customer management system. It's a really interesting use case for geospatial, and I think that you'll enjoy the conversation. So thank you, Alistair. Thank you, Mapsimize. It's much appreciated. And that's it for another episode of the Mapscaping Podcast. My name is Daniel, and I would love to hear from you. So please reach out to me. You can find me on social media. Just search for Mapscaping. On LinkedIn, just search for host of Mapscaping Podcast, and you'll find me. It would mean a lot to me to hear from you, hear your thoughts, opinions, suggestions. It really helps me shape the direction of this podcast. I'll be back again next week with another episode, so tune in then, and we'll talk then. Bye.